All right. So, in this particular part of the PIV lecture, we are going to talk about perspective projection. Now, as you know, that in most of the cases, the particle that is there in the flow field, um, for example, if the particle, if this is the flow field and if this is the laser sheet that is illuminating the flow field or part of the flow field, okay, the particle may not just move in the plane of the light sheet. So this light sheet has got a finite thickness. So the particle may not actually move in the plane of this light sheet, but may actually have a velocity component which is perpendicular to the light sheet. That means it might have a z component, for example. All right. So, in order to fully explain the influence of the velocity components perpendicular to the light sheet, the location of the image points in the coordinate system x, y, and z, okay, the XYZ that the lens actually images needs to be taken into consideration, because this is what the lens is actually imaging. So this is the imaging of a particle within the light sheet in the recording plane. All right. So if D defines, okay, the particle displacement, for example, between two light pulses, okay, then the components of D will be dx, dy, and dz, right? There will be three components. Okay. So in other words, and we will see in the next one, so as we can see that the relationship between the location of the corresponding images in the image sensor plane due to the recording of a particle at x equal to xi and x equal to xi prime is actually a little different. As you can see, this is what the image of the particle actually looks like, okay, in the imaging plane, okay, where D actually denotes the displacement. So we'll see in the next slide what it exactly means. So this is your camera, this is your field of view, this is your distance of the object, okay, from the PIV camera. All right, and this is what we are actually recording. So this is what happens. So if you look at tan alpha, it is xi prime by z naught. So if you look at this one, this angle, the tan alpha, it is xi prime divided by z naught, okay, which you can see over here. This z naught is basically this small z naught, okay. So this is the angle that it actually makes, okay. This is the angle from the axis, from the optical axis. So the image displacement, which is D, xi prime minus xi, corresponds to a certain particle displacement. Okay. So what it looks like is that the image displacement is actually this. Okay, xi minus xi prime, okay, and corresponding to a certain particle displacement, which is actually capital D. This is the image displacement that we see, okay. The image displacement corresponding to this particle displacement that we see over here. Remember the small xi, the small x corresponds to the image, while the capital X corresponds to the object. So you can see, understand that this displacement that you are measuring, xi minus xi prime, actually corresponds to some particle distance that the particle has done in the light sheet, in the object plane. So in other words, if your xi minus xi prime is therefore given as, so capital D is the actual particle displacement. So it is a magnification factor multiplied by these quantities. So you can see there is an xi displacement and then there is a yi displacement, both on the image plane. Okay, they correspond to the actual particle displacement modified by the magnification factor and the out of component particle displacement, which is the component of the particle displacement which is perpendicular to the light sheet. Okay, so it can be seen from these two equations, which is 2.26 and 2.27 from Marcus Raphael's book, that the particle displacement in the z direction influences the particle image displacement. So if the particle moves in the z direction, what happens? It influences the actual image displacement that happens in the x and y plane. Okay. So especially for large magnitudes of xi and yi, the edges of the observation windows, this is a very, very important factor. So this effect, what it does, it incorporates an uncertainty in the measuring the in plane velocity components, because it cannot be separated from the in plane velocity components, because remember, we are using this to calculate the in plane velocity components, but then you have already, the magnification factor, but there is no one-to-one correspondence with the displacement in the x direction and the y direction of the actual particle, because then you have this out of plane component which actually comes into the picture, which is dz into xi prime divided by z naught. Okay, so this introduces what we call a systemic error. Okay, if we assume that the PIV only measures the in-plane components, even for large viewing angles. So larger the viewing angle, which is larger is this tan alpha, okay, larger is this tan alpha, okay, you will have a more, this value will go up. As a result of that, you will have even even more systemic error creeping into the system. Okay, so one way to reduce this error is to increase the camera standoff distance z naught, thereby reducing the viewing angles. So one way of doing this to reduce this error is basically to reduce the camera standoff distance z naught, and thereby you reduce the viewing angle. So your field of view is very, very important, because towards the edge this effect becomes quite substantial. Okay, so this is the perspective. Okay, now let us look at the cameras in particular, that what are these cameras do and what are they made out of. So first and foremost, normally PIV cameras can be CCD cameras, especially low speed PIV cameras. So in general, what happens is that CCD camera actually has an electronic sensor that can convert light into electric charge. Okay, in other words, the photoelectric effect. The CCDs can come in the form of a line. There are line scan cameras, or it can be arranged in a rectangular array. Okay, so an array of a CCD camera, if you look at it, consists of this small, what we call pixels. Okay, so the individual CCD element is called a pixel, and the pixel is usually 10 micron by 10 micron or 100 pixel per millimeter. Okay, so how does it actually work? Okay, it is built, the CCD is built on a semiconducting substrate. Typically it is a silicon substrate, okay, with metal conductors on the surface. So these are the metal conductors on the surface, okay, and and then there is an insulating oxide layer just below it. Okay, then a small voltage is applied between the metal conductors and the P layer. Okay, and that actually generates an electric field within the semiconductor. So you understand, so there is a semiconductor, okay, which is now covered by an oxide layer and a metal conductor. So once you apply a small voltage between the metal conductors and the P layer, okay, you generate an electric field within the semiconductor. Okay, the characteristic of a pixel is also called its field factor. So we'll get to that a little later. So as light impinges, you basically release electrons, and so basically you have an accumulation of charge which depends on the how much amount of light it is actually gathering. So the characteristics of a pixel is also called its field factor or aperture, which is basically defined as a ratio of its optical sensitive area to the entire area. We'll see why that is important, because optical sensitive area, and then it can have a larger area which is not optically sensitive, especially the CCD cameras when it has got blind pixels also, okay, where it basically shifts in between measurements. So the value can reach 100% for special scientific grade cameras, and it can be as low as 15% for interline sensors. So 100% of the camera may actually cover the whole area. Okay, so we will see a little bit of those examples later. Then of course, we have now the advancement of the CMOS sensors. Now The main advantage is that each CMOS, unlike the CCD pixels, there are photodiodes in the CMOS sensors, and this can be controlled. So the fundamental principle is shown in this figure, which is 2.65. Here you can see that each individual pixel contains an electronic circuit. So you can see each pixel is this, and it contains an electronic circuit. Okay. So this is called an active pixel. So the active pixel architecture with individual access, so it offers individual access to each pixel, and it allows you to basically, integrate fundamental camera functions like amplification, nonlinear signal transformations, and analog to digital conversions on the chip, etc., etc. So you can have individual control of these pixels. So these are basically photogates or phototransistors. Okay, so if you now look at the spectral characteristics of a camera, this is also important. So similar to a photographic film, the digital sensor also has a sensitivity and it has got a spectral response also. Okay, so the pixel sensitivity is also called the quantum efficiency of the camera. It is defined as a ratio of the number of generated and collected photoelectrons and the number of incident photons. So you can see the number of photons are incident and you generate certain amount of photoelectrons. So what is this ratio? More the number of photoelectrons that are released, better is the quantum efficiency of the camera. Okay, so if you can see, this is quantum efficiency, this is with wavelength. You can see that these are different CCD cameras. Okay, forget about what they are. I mean, there is CCD with micro lens, with NIR enhanced, and a lot of things, back thinned. Okay, so you can all see that, at around 532 nanometer, where an Nd:YAG laser actually operates, the cameras have their peak quantum efficiency. Remember, the quantum efficiency drops on both sides quite rapidly, particularly in the UV. In the UV region, the quantum efficiency is rather low, and so is in the near IR region. So if you have measurements, if you have radiation, which you are collecting at these kind of wavelengths, okay, then your camera will not be sensitive enough because its quantum efficiency will be rather low. Or in other words, the number of generated and collected photoelectrons will be low. Okay. On the other hand, for PIV, because most of the time we use Nd:YAG laser, which is 532 nanometer, this is the best case. So you can use the maximum quantum efficiency range of the camera to do this. Okay, so in order to reduce susceptibility to infrared light, many cameras comes equipped with an infrared filter so that they cut off the light which is beyond a certain wavelength. Okay, so that is also done in these cases. Okay. So how does a PIV recording actually happens? So as you know, the PIV recordings now can be classified into two categories. One is that you can capture the particles multiple times on a single frame. So if you look at this figure over here, you can see this is a single camera exposure, single frame, single exposure. You can see that if you keep the time of exposure too long, this particle will become like a streak. Okay, so this is the camera opening and the closing time. Okay, so T and T prime. Okay. On the other hand, if you have a single frame multi-exposure camera, okay, that means the camera is still a single frame, but it has got multiple exposures. Okay, so you can get or a double exposure. So the camera is actually exposed for two selected times, the T1 and T prime. You will see these two particles. If you take the same image, you will see the particle actually moving. All right. You can also do what we call a double frame single exposure. Okay. So in this case, the principal distinction is that the single frame approaches do not retain any information on the temporal order. So there is a direction bias or a direction ambiguity. in the recovered displacement vector. In contrast, when you do multi-frame single exposure, the PIV recording, it preserves the temporal order. You can also do it in double frame mode, okay, double frame single exposure mode, okay, or you can do double frames. This is double frame single exposure, this is multi-frame single exposure, and this is multi-frame double exposure. So you can do all these kind of things using the current cameras that we have. Okay, so let's look at the digital cameras. So in this section, we describe the CCD and the CMOS based cameras, which we have already covered a little bit. And we are also talking about flash lamp pumped double oscillator ND-AG lasers, which provides high pulse energies. And it has got a rep rate that matches with the framing rate of the cameras. Typically 10 Hertz, the cameras also can go up to 10 Hertz. You can go to high speed lasers. Your camera can also are very high speed these days, especially the SCMOS cameras. Okay, so the CCD cameras that are used for PIV has two advantages, important advantages. One is that they have increased spatial resolution. The second is that the electronic architecture permits two PIV recordings because you have to get two frames. Okay, and these can be separated by microseconds or even nanoseconds, and it can be recorded by the same camera. Thus, the same camera can take two images or two frames which are separated by microseconds or even nanoseconds, and you can record it on the same camera. So that is the advantages because you need two frames. So it should be noted that in contrast to most CMOS sensors, what happens here, let me try to see that this is the pixel array of a CCD camera. What you see at the bottom is basically called an analog shift register. So what happens is that in contrast to CMOS sensors, each array is read out, okay, sequentially in a two-step process. Okay, so after the sensor is exposed and it collects certain amount of accumulated charge, which is basically the photoelectrons. Okay, these electrons are shifted vertically, one row at a time. Okay, vertically, one row at a time. Okay, into a masked, so this is the part where it is masked and it is optically blind analog shift register on the lower edge of the sensor. Okay, and each row is then clocked pixel by pixel to using a charge to voltage converter, and thereby provides a voltage for each pixel. So depending on this image transmission format, the readout of the sensor can be sequential, which is called progressive scan, or interlaced, in which first all odd rows are read out before the even rows are attempted. Okay, so you can see these charges are now shifted to an analog register from where they are basically read out using a charge to voltage converter. Okay, so this is how the principle actually works. Okay, and depending on the employed image transmission format, the readout of the sensor can either be sequential or interlaced. Okay, so if you look at this as the standard CCD, this is like frame transfer CCD, this is interline CCD, and this is full frame interline transfer CCD. So you can see that this is what it says, that these are the pulses. Okay, these are the laser light pulses and how the camera is actually open between the two pulses. Okay, so you have frame transfer CCD, so this is where it is open, and this is the period where the charge transfer actually happens. Okay, so this is the period. So you can see that these are the timing diagrams, okay, that how particle illumination charges have to be produced to, to see what is going on. So when it's interline, this is even, and so this is how this is actually read out. All right. So you can see that in the case of frame transfer mode, what happens is that the lower half of the rows are all masked off and cannot be exposed by the incoming light. So once exposed, the rows of the accumulated charge, which is this one, transfers the charges rapidly downwards into this masked off region with about 1 microsecond per row. Okay, and then that is converted to an analog charge to voltage register, and this becomes now accessible for the next image. So in the case of an interline CCD, interline transfer, what happens is that if you look at it very carefully, you will see that each pixel has got its own storage cell. Okay. So each pixel has got its own. So this is the light sensitive area and this is the vertical register. Okay. So that means there are blind pixels that allows immediate transfer, immediate storage of the accumulated photoelectrons. So as soon as this is exposed, it kind of stores in this vertical shift register. The storage pixels are then located in between the pixel rows, hence the name interline. So there will be another light sensitive pixel after this, and then again a vertical shift register to the left of it. Okay, the transfer of accumulated charge to the storage cell can be accomplished in sub-microsecond range, which effectively allows the capture of two separate images in a very short time interval. So you understand, this is where the photoelectrons accumulate. They are quickly transferred from here to here, from here to here, the vertical shift register, right? And then they are taken out. So you have alternate rows, alternate columns here, which are basically not photosensitive. They are masked off. Okay, blind folded pixel, as we call it. All right. So that is how this transfer mechanism actually happens. Okay. And the CMOS camera we have already covered. How does that actually do? Okay. So typically, so just to go back, just look at this diagram properly, because this is what you need when you actually do your PIV measurement. You need to synchronize your camera and laser properly, and you should also know that how fast the charge transfer actually happens, so that determines the time frame between the two pulses. This also allows you that shorter the time distance or the time interval between the two pulses, higher is the velocity that you can actually calculate or you can actually measure. So that is one area in which you have to look at different transfer techniques like frame transfer and interline CCD transfer we talked about just now. And this is a mixture of the two, the full frame interline CCD transfer. We have already talked about the mechanisms, how the charges are actually transferred and making it possible to take the second image. And we also talked about that what is a single exposure, double exposure, and stuff like that. Okay. And please pay attention to these kind of figures, because this is how that thing happens. And CCD camera, CMOS cameras, we have already done quite a bit of a work on the CMOS cameras. We have explained that it is basically, if I go back, it is basically this. Okay, so each camera has got its own electronic circuit. So it allows us to do this, but it also suffers from noise issues and low quantum efficiency. And remember what quantum efficiency was? We kind of, showed this here. So you can see the quantum efficiency. Scientific CMOS cameras are getting there, okay, in that particular category. But normally you will see that there are CCD back thin CCD, which can have much higher quantum efficiency, and you can collect therefore more light. Your image intensity becomes huge. You can have higher viewing angles in that particular case. Your zone of illumination will be brighter. Also remember one thing, that the out of plane component of the displacement actually is embedded in your image displacement. Okay, as a result, this leads to what we call highly systemic errors in the system. Okay, now in this next class onwards, we are going to do the mathematical background of statistical PIV evaluation. So far, we have talked about how to take the image, how to create the laser sheet, what are the caveats over there. Now we are going to look at that how, if we take the images, and how to process the images, and how the PIV recordings, as we know, they are already subdivided into interrogation areas, and how these interrogation areas can be finally used to calculate the velocity. So the first mathematical description of statistical particle image velocimetry was given by Ron Adrian. This early work from 1988, he used the autocorrelation methods, and later on it was expanded to the cross correlation, and a careful and complete mathematical description was given by Westerville, and and Adrian and Westerville published the most comprehensive book on particle image velocimetry in not, it is about 13 years ago. Okay, so this is a practical handbook. If you want to know about more on the particle image velocimetry per se, you have to go through those kind of books. Okay, so in the next lecture, what we are going to do, we are going to start looking at the particle image locations and then try to see how those image locations can be used and how the interrogation windows can be used to calculate the image intensity and then take it forward for the velocity calculations. Okay, so we stop here and please go through this lecture properly. We have covered a lot from perspective projection to the sensors that are used, to the definition of quantum efficiency, how that charge transfer actually happens, okay, and what are the different modes of charge transfer that we can have, especially the interline, the full frame transfer. So you should look into all of these things, okay, before you move on to the next.